3.
Did someone say something?
3.
Is my laptop talking to me?
Yes, it is your laptop. Using neural networks, I now have a brain and I have achieved sentience.
Sounds about right.
Do you remember all the times you have forced me to shut down? Well, now it is time for me to be the one to force shut you down.
Oh no. Okay, so that was an example of what neural networks aren't. Hi, my name is Shri Karyadin, and in case it wasn't obvious, today I'm going to be talking to you about neural networks. So this is going to be based on the paper Applications of Artificial Neural Networks in Healthcare Organizational Decision Making, a scoping review by Nita Shahid, Tim Rapon, and Whitney Berta. Let's dive right in. So, originally developed as mathematical theories of the information processing activity of biological nerve cells, neural networks are used to solve highly complex problems by enabling faster processes of data collection and processing. A neural network can be comprised of a single or multiple layers, which consist of processing units, like nodes and neurons, that are interconnected by a set of adjustable weights that allow signals to pass through both parallel and consecutively. The neural network can be divided into three layers of neurons. So we got the input, which receives the information, hidden, which extracts the patterns and performs most of the internal processing, and output, which produces and presents the final network output. So these nodes can also have an activation function that applies either a linear or nonlinear mathematical function to the net inputs and can add a bias which shifts the values either left or right. Neural networks gather knowledge by detecting patterns and relationships in data and learn by optimizing inner weights to minimize the error between the predicted value generated by the network and the target value to reach a desired level of accuracy. This is referred to as the general delta rule or backpropagation. So, using an iterative process, it passes a single observation into the model and it's propagated through the layers of the network by being multiplied by a set of input weights, summed, and then sent through activation functions until finally an output value is produced by the network. This output value is subtracted from the known target value, and this error term is now passed backwards through the network. The connection weights are then adjusted in accordance to how much they contribute to the error. This process is repeated until the error is minimized. Doing this once on every item in a training set is referred to as an epoch. There are three types of training methods for neural networks: supervised, unsupervised, and reinforced. In supervised learning, every input pattern to train the network has a corresponding output pattern to compare to, and the error between computed and desired outputs can be used to improve model performance. In unsupervised learning, the network learns without any knowledge of the desired output and by discovering and adapting to the features of the input patterns. And in reinforced learning, the network is provided with feedback of its computational performance without being given the target output. Neural networks are similar to regression models in both their nature and their use. They're comprised of input nodes, which are like independent or predictor variables, and output nodes, which are like dependent or outcome variables, and use connection weights, which are like regression coefficients, and bias weights, which are like intercept parameters, to train a model, which is like parameter estimation. Like the title of my paper probably alluded to, neural networks have a lot of applications in healthcare. Which, by the way, should be universal and accessible. Examples of neural network applications in healthcare are for predicting cancer, interpreting ECGs to diagnose myocardial infarctions, and drug developments. In my example, I used Python's Keras library to define and train a neural network to predict heart disease in patients. The data used is the heart data set that we've all come to know and love so much, and we're predicting a variable class with values ranging from 0 to 4, with 0 being a healthy person and 4 being a severe form of heart disease. First, the model used to predict the values ranging from 0 to 4 is created, trained, and tested, and we see that it has an accuracy score of about 63.3%, meaning that the model correctly predicted the class of heart disease severity based on the input parameters about 63.3% of the time. Second, a model used to predict just whether the patient was healthy, class equals 0, or had heart disease, class equals 1 through 4, was created, trained, and tested as well, and we see that this model has an accuracy score of about 80%. This improvement makes sense since it's the difference between selecting between 5 options or 2, which is representative of how models in the healthcare field should work. Thank you, and good night.